we completed actually Zeeman effect in both normal Zeeman effect and anomalous Zeeman effect. Then we studied this under strong field and weak field case in both cases. So normal means that spin was not included, and in this case here spin is not equal to 0. For strong field, we concluded B is much greater than spin orbit interaction, that was W, which was fine structure actually interaction, and for this B was less than for fine structure component. So this gave us the component ML plus 2ms shift. This gave the component mu B GJ. Okay, GJ. And this was simply mu BB normal. Just to remind of all those. So I will give you some examples. We will discuss some examples today, and to finish this topic. And I will give you an example that with diagram that splitting off to D level of sodium when number 1 in weak magnetic field and strong magnetic field, and you have to show it in the diagram. Weak magnetic field here, strong magnetic field this. Both cases are of anomalous Zeeman effect. So let us take it in first weak magnetic field. I will take the weak magnetic field first. Weak magnetic field, and you know that the interaction energy, that is mu B mj gj. There will be also, I think, and the interaction energy term will be here it is. This is a strong field, this is the weak field, so it is this. Mu B mgj. The shift is accepted, this excluding this B because B is constant, so we can calculate the shift here. And
सर शिफ्ट तो म्यू बी mj ही है.
yes, it is mu B mgg, and mu B is also constant, so what changed actually, it is mjgj. And so we have the level is given, that's called, it is actually fine structure level. So we have it is 2D, and let us suppose first we have 3/2 because for D we have J will be equal to this 3 by 2 and 5 by 2 for this this D level. So first we will take case of 2D 3 by 2 level, fine structure term, and
सर 1/2 भी होता है,
yes,
1/2 भी है, D उसको भी J वेरी
I
होता है.
yeah, I'm taking only the fine structure interactions because of the fine structure splitting.
Okay sir.
Okay, so 2D 3 by 2, because L will be equal to 2, S will be equal to 1 by 2 for single electron, and J will be equal to 3 by 2. Okay, and this is the 3 by 2 level. For D 5 by 2 level, because it's 2D, so you have 2s plus 1 is equal to 2. It gives s is half. So that is one
Yes sir.
electron. Okay, and 2D 5 by 2, and for D, L is equal to 2. So L plus S to L minus S. So it is 3 by 2 and 5 by 2. 2D 5 by 2. So L is equal to 2, S is equal to 1 by 2, and J is equal to 5 by 2. These are the two different levels. Now the components in case of weak field, it is 2J plus 1. So number of components, number of lines, that is 2J plus 1. So I can write 2J plus 1 equal to how many for this? It is 4. This is 6. Okay. And for this case, the GJ, if you calculate, GJ will be 4 by 5 here, and it will be 6 by 5 here. If you calculate GJ, and GJ is given by 1 plus J plus 1. This is how we calculate this value here, 6 by 5. Let me change the pen. And MJ for L equal to 2, MJ, M goes to J equal to 3 by 2, 1 by 2,
-2
0, minus 1 by 2,
अच्छा,
minus 3 by 2. So 5 values of MJ.
-3/2.
Okay.
Yes sir.
Similarly for this, we have 5 by 2, 3 by 2, 1 by 2. There is no 0, sorry. We don't have MJ 0. We do not consider 0 actually, because that level is separated corresponding to 0. 5 by 2, 3 by 2, 1 by 2, it is minus 1 by 2, minus 3 by 2, minus 5 by 2. And now shift is GMJ, GJ, MJ. These are the shifts.
GMJ.
Okay, so that you can calculate from here, GJ into MJ. Yes, this multiply these two. So that is 6 by 5, 2 by 5, minus 2 by 5, minus 6 by 5. This will be 15 by 5, 9 by 5, 3 by 5, minus 3 by 5, minus 9 by 5, minus 15 by 5. Okay, so these are 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 6, 6 plus 4. So the 10 levels actually total in 10. Now how to draw these? Now we have to draw. Since we have found the number of values for the corresponding values of GJ, MJ, how to draw? Let us take this 2D 3 by 2. Okay, for lower energy, and this is no field because of including the spin orbit interaction in case of weak field case. Okay, in weak field case. So when we have no field, I can write it as, you have how many levels corresponding to MJ value? We have this 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. See, these are 4 levels. So it is, if it is mj here, I will write gj mj here, and I can write mj corresponding to this level is minus 3 by 2, minus 1 by 2. This is 1 by 2. This is 3 by 2.
3 by
And what
2.
is this? This is 6 by 5. Corresponding to this. Corresponding to this, it is 2 by 5. Corresponding to this, we have already calculated them above. Minus 2 by 5. And corresponding to this, it is minus 6 by 5. So this is actually we have calculated here. I am putting up these values. These. Okay. Now taking 2d 5 by 2. 2d 5 by 2. So how many levels? 6 corresponding to mj values. Mj values are there. These are the mj values corresponding to these 6 levels. Now let us draw them.
सर इन दोनों के बीच अगर स्पेस देखनी होगी मतलब
Yeah,
लेवल
you
इसके
can
बीच वो
calculate.
कैसे
Just change the values of this mj. Put up the values of gmj. That is the space. There's a shift. This is a gmj, and you can put up with mu b there and b. What is shift? It is g mj mu b b. This is the shift. So gmj is the variable that you have calculated, and mu b will remain constant. Okay, so it will be minus 6 by 5. So minus 6 by 5 to this minus 2 by 5. So you can calculate the shift difference separation between these two by taking the values of these two different levels. Okay, for mj, j plus 1 and j. Okay, so you can calculate the separation distance from these values. These. And they are not equal.
Yes sir.
I'll draw some right here because it will go away. Change again the color. So corresponding to this, it is minus 5 by 2. This is minus 3 by 2. This is minus 1 by 2. This is 1 by 2, 3 by 2, 5 by 2. And here it is 15 by 5. This is 9 by 5. This is 3 by 5. This is minus 3 by 5. Minus 9 by 5. This is minus 15 by 5. So this is how we draw the energy levels in case of weak field Zeeman effect. And when we have a given fine structure level. When we are given with the fine structure level, actually we will do more examples for this. And this is no field, this is weak field in this case. I'll just zoom out so that you will be able to see it. We will see how to draw the transitions. Then we have to see the transitions as well, that we will do also in the next one. Let us take first the strong field, Zeeman effect. So in strong field case, we have same table. You will make the same table. Let this be, this is term, sorry. Term here. So it's 2D term because there is no spin orbit interaction. The external field is very strong. So we are ignoring that 2D interactions. So it is, sorry, internal interactions. And this is 2D term here. There will be only 2D, no spin orbit interaction here. So number of levels in this strong field case is 12 plus 1, 2s plus 1. So this is how the number of levels is given. And ML, and one important point is that you will find that it is same for both weak and strong field. Levels will be same, but some of them will be degenerate. We have to see the degeneracy then and shift. That is
Yes, sir.
ML plus 2 MS. Now 2D, we know that J is equal to, let us, J is not equal because we are not taking the spin orbit interaction, so we don't have any J here. L is equal to 2, S is equal to, now 12 plus 1, 2S plus 1 will be 10. L is equal to 2. 2 2s are 4 plus 1 is 5. 2S is half. So it is 2. 5 2s are 10. So these are 10 levels. And ML values will be 2, 1, 0, minus 1, minus 2. Now MS values will be 1 by 2, minus 1 by 2, 1 by 2, minus 1 by 2, same 1 by 2, minus 1 by 2, 1 by 2, and minus 1 by 2, minus 1 by 2. And shift will be now ML plus 2MS. ML here 2MS. This is, you can write the lowercase ML plus 2MS. So ML2 plus MS is plus half and minus half. So you have two values corresponding to this. One for plus half, one for minus half. So in one case it will be 3 and it will be 1. Okay. In this case it will be 2 and 0. In this case it is 1 minus 1. It is 0 minus 2. It is minus 1 minus 3. So still these levels here, anywhere where you find the same ML plus 2 MS value, those will be degenerate. Let us see how to draw them. This is 2. This is 2D. There will be somewhere 2D. I will not, because we are not concerned about if you not draw those 2D 5 by 2 and 2D 3 by 2. So this will be 2D 5 by 2 somewhere here. Higher J, higher L, higher energy. 2D 3 by 2. This is how they should be there. This is 2D. So now from there we have this. We are concerned for this. Sorry, this level. This is just for reference. So we have how many levels in? Level is 10. Some of them are degenerate. Let us first. So those levels for which ML plus 2 MS is same, those will be of the same energy. This is the main conclusion from the weak field, strong field Zeeman effect. That is also called as Bastian-Back effect. Okay. Now see here. So this is here one level. I will draw the order actually, ML plus 2 MS. So let this be ML plus 2 MS. So what is it? It is 3, 2, 1. 1 is 2 times there. See here. 1, 1. Okay. 0, 0. These are 2 times. There are no other 2 values which are same. These are the only values which are same actually. Okay. So that's why I'm writing the 1, 1.
minus 1 भी दो बार.
Yes, minus 1 is also there. Good. So this minus 1 is also there. So 1, 1, we have 0, 0, we have minus 1, minus 1, we have minus 2 and minus 3. Is it okay?
Minus 3.
Yes.
Yes, sir.
Yes,
Okay.
sir.
Now draw the lines. These are the lines. These will be 2 lines, but they will be of same energy. Here, these will be 2 lines, but they will be of same energy. Here, these will be 2 lines, and these will be of the same energy. Okay. And this is a single line, and this is the another line. So you can draw them like this. No, not necessary to join this, but you can show them like this. So these are 1, 2, 2, 2 plus 4, 6, 8, 9 and 10. So these are 10 levels which can be drawn by taking into effect the perturbations because of the strong field Zeeman effect. Strong field Zeeman effect case. Okay. So this is how we draw the lines in weak field. This is no field. This is strong field. So any issue up to here?
No, sir.
Okay. Let us move to another example. I will give you another example. This is the simple one. Discuss the Zeeman splitting of the resonance line one, sorry, not this, D1 and D2. These are the D1 and D2 lines of sodium. What are the resonance lines? I have discussed. We have defined a resonance line already. What it is. So these are those lines actually for which this L is same almost. The transitions between the two lines where the L remains same, where L does not change, but J changes actually because of S. So we will consider these two lines. So the transitions between these two lines are represent actually D1 lines. So line is actually what you observe in the output spectra. Line is a transition. This is a two lines. There's a transition between two lines, so that will be give you line that is represented as D1, and another line similarly. There's another line from some another level that will be represented as D2. So these are named as D1 and D2 lines actually. Okay, and because there is different value of this J. Now how to draw these lines and how to draw this Zeeman splitting.
Sir, repeat.
Yeah, so I'm saying that this is a name of the line spectra. So because when you discuss line spectra, there are different lines in the spectra. So those lines are named actually. One line among them in this case of sodium is corresponding to a particular transition. So that transition is given, and corresponding to that transition, that line is named as D1, and that transition is 2p 1 by 2. When there's a transition between these two lines, these two yes, terms, this is D1 line. Okay, and when there is this 2p 3 by 2 to this, so it is D2. Okay, so these are how the lines are named actually between different terms. So when transition occurs from
Okay.
2p half to 2s half, it is named as D1. When it's 2p 3 by 2 to 2s half, it is D2. And any transitions between these two lines will be D1 and D2 accordingly. Now, for weak field case, in the case of Zeeman, anomalous Zeeman effect for weak field case, I will discuss them in the terms of weak field case because we are considering J here. When we take it into consideration the J, which is L plus S, so we are taking into consideration both external field as well as the internal interactions, that is spin orbit interaction, which we ignore in strong field case. So here I am not ignoring. When we are not ignoring, it becomes anomalous and weak field case. Now, similar pattern as we did it in the above example. So this is term, this is number of levels, Zeeman levels, this is 2j plus 1, this is G, this is mj plus j up to minus j through 0, sorry, minus j plus j to minus j, this is shift, that is G, j, mj, that's a shift. Now term is 2s half. Then we have 2s half. For 2s half we have L is equal to 0, S is equal to 1 by 2, J is equal to 1 by 2. We have 2p half. So L is equal to 1, S is equal to 1 by 2,
1 by 2.
and J is equal to 1 by 2.
1 by 2.
Okay. Now it is 2p 3 by 2. L is equal to 1, S is equal to 1 by 2, and J is equal to
3 by 2.
2j plus 1 levels. So to give it the value here, so it is 2, 2, 4. Okay. Now Gj, this is 2. It will become 2 by 3. This is 4 by 3. Okay. Mj, so plus minus 1 by 2, plus minus 1 by 2, plus minus 1 by 2, plus minus
1 by 3.
3 by 2.
3 by 2.
Okay. Yeah. Now shift is plus minus 1, plus minus 1 by 3, and plus minus 2, plus minus 2 by 3. So this is actually Gj into Mj. So this is the product of these two.
Yes, sir.
Now we have 2, 2, 4, 4, 4, 8 levels actually. And now we have to see how many transitions are allowed there. So when you need to find the allowed transitions, what you will use? Selection rules. So you will use actually the selection rule. Okay. Now selection rule for these are dipole transitions. Delta Mj is 0 plus minus 1. And remember that Mj equal to 0 to Mj dash equal to 0 is not allowed.
Not possible.
Then you are done. Let us first draw the energy level diagram. To S half. Two P half. 2p 3 by 2. Okay. Now these are in. Now what is the d1 and d2 line actually? So 2p half to 2s half is d1.
D1.
These are two d2 lines in absence of external field. Now when you place this system into external field, instead of these 2 lines, you will see 10 lines. Okay, because of the interactions. And first we will draw the this again here. Mj, Gj. Okay, indexing just for the indexing purpose. So this is Mj is here minus 1 by 2. This is plus 1 by 2. And this is 1. This is minus 1.
Minus 1.
Okay, for Mj, Gj. Gj is, we have calculated all these values in the above table. This is the new normal line, zero field line. So we have 2 half. Again, we have these 2 lines here corresponding to 1 by 2 minus 1 by 2. This is again 1 by 3, and this is minus 1 by 3. Okay, that's again. Now here we have 4 lines, sorry.
4.
And this is 3 by 2, 1 by 2, minus 1 by 2, minus 3 by 2. Corresponding this we have 2. This is 2 by 3. This is minus 2 by 3. And this is minus 2. Okay. Now you have to draw the transitions. So apply selection rule. It will be easy for you. And when you apply the selection rules, okay, the transitions will be, see how many transitions will be there. There will be almost, I think there are 10. So there will be 4, 6, 8, and 10 lines will be there. Okay, because we have already seen that 10 lines will be there. Now we have to draw the 10 transit lines in the case of using selection rules. So first, corresponding to this D1 level, D1 line, you have one here,
1/2 to 1 by
one
4.
by here.
Yes, sir.
Okay, and then you have here, here. Okay, this is okay. There is no issue in this. Apply selection rule, you will be physically correct. It will be correct using those
Yes,
selection
sir.
rules. So these are the D1 liners. So you are 4 liners instead of 1 when you place it in the external magnetic field. Now see this. We have to use the selection rules. So let us start from this. It is minus 3 by 2. 2. I can go, it is minus delta mj. So delta mj will be equal to higher minus 3 by 2 minus 1 by 2. What is that? So minus 4 by 2, that is 2, which is not allowed. So this transition is not allowed. Minus 3 by 2 to minus 1 by 2. So the only transition will be, that is this. Minus 3 by 2. Sorry, not this. Okay, I'm done wrong. This will be allowed.
So minus 1 by 2.
Plus 1 by 2. So it is minus 2 by 2.
Yes, sir.
That is minus 1.
Minus 1.
Okay, so that transition is allowed. So from minus 3 by 2 to minus 1 by 2, this is allowed. Okay, but from minus 3 by 2 to plus 1 by 2, it is not allowed. Because that is this. This is minus 3 by 2 and minus 1 by 2. Because delta we are taking the difference, so we are subtracting it. Because of that minus, this becomes plus here. And this becomes
Plus. Minus
Yes,
1.
sir.
so that's why these are not that one is not allowed. Now similarly, if you draw the other transitions, I will draw them by changing the color. So we have another transition here. Sorry. This will be also allowed. We have
Yes,
this
sir.
one minus 1 by 2 to
Minus 1 by 2.
this
1 by 2.
minus 1 by 2. So is this allowed? It is 1 by 2 plus 1 by 2 is 2.
Yes,
It
sir.
is 1. Yes, it is allowed. No issue in that.
Yes, sir.
Okay, so this is allowed. And we have another transition here from this level. This level we have another transition. This will go directly to this. 1 by 2 minus 1 by 2 is 0. That is also allowed. Okay,
Yes, sir.
there is one more transition from this top level.
3 by 2.
That goes
Minus
this here. 1 by 2.
plus 1 by 2.
Okay, 1 2 3 4 5 6 7 8 9. One more is left. Can you draw that? What will be that? So that will be, we have one transition from this level. There's one more transition from this level actually. This,
Minus 1 by 2 to
that
minus
is
1 by 2.
there's only one.
Minus
Sorry,
1 by 2 to minus
that is
1 by
one
2.
from this. Yes, from minus 1 by 2 to
Minus 1 by 2.
minus
Minus
1 by
1 by
2.
2.
Yes, minus 1 by 2 to minus 1 by 2. Good. So it is from minus 1 by 2 to minus 1 by 2. Good. So I can draw it here. Okay. So these are how we draw the transitions. So this is actually, these are the D2 liners and this is D1 lines. These are D1
D1.
lines. Okay. And you can do more examples for this. Let me show you another one. I will. So for weak field case, let us take an example of 1F3 to 1D2. Or I will shift it on this. Let us take another one. it is 2d 3 by 2 to 2p 1 by 2. And it's easy for you. I think you can do it easily. There's no issue in that. I will give you some
Okay,
more.
sir.
This is easy. So let's take it another way. 2d 5 by 2 to 2p 3 by 2. So this we have done already. 2d 5 by 2 to 2p 3 by 2. This we have done. And 1f. Okay, I think we have done it. There is no issue in this. This we have done. Okay, so I think Zeeman effect part we have done. I will give you one example from spectral terms. Let us see that spectral term. One example. So this you have done. This is no issue. So compute possible terms. I have given this actually assignment, but nobody has done it. And energy levels. For a configuration that is with 3 electrons, so it is 2p, 3p, and 4d. 2p, 3p, and 4. So a good example, a simpler one. Find the magnetic moment in Bohr magneton. Magnetic moment in Bohr magneton of an atom in 3p2 state. This is a spectral term 3p2. 3p2 state. Any idea how you will do it? You have to find the magnetic moment. Since the J value is given, so you have to take the mu J. You have magnetic moment in spin magnetic moment. You have mu L, orbital magnetic moment. When it is J, you have total magnetic moment, that is mu J. And how it is given by? It is G E by 2m into J. Where this J is under root of J into J plus 1 h cat. So can you do
Okay,
it?
sir, करेंगे.
Yeah, just
Yes,
find the
sir.
answer for mu J.
Okay, sir.
There is another for ground state of chlorine atom. Ground state of chlorine atom. Chlorine atom. So find it is, yes, find ground state. You have to find ground state of chlorine atom. Find the ground state of chlorine atom in 2p 3 by 2 state. So you have to find, don't let me know. I will not tell you. So you have to show that it is 2p 3 by 2 and then find its magnetic moment. Find its magnetic moment, and then you have to also find into how many substates this ground state will split when you place it in weak magnetic field. So find number of substates when chlorine atom is placed in weak magnetic field. I think you should be able to do this. Simplest one. This is a simple example you can do.
Try करेंगे.
Okay. Anyone? Anything else?
Okay.
Okay, I think this is enough for today. We will discuss stock effect tomorrow.